welcome to page 2, and now we're going to talk about the unit tangent vector. And so remember, whenever we're trying to find the unit vector, we're just going to divide by the magnitude of whatever vector we have. So it's the same thing for the unit tangent vector. We're going to take our tangent vector, which is r prime of t, and we're going to divide that by the magnitude of r prime of t. Right? And so that's the unit tangent vector. So example 2, we just want to find the unit tangent vector at the point with the given value of the parameter t. So to find the unit tangent vector, what we're going to do is first find the tangent vector, so we need to find the derivative. So r prime of t. And when we do this, the derivative of sine squared t is going to be 2 sine t cosine t I plus the derivative of cosine squared t is going to be 2 cosine t. Derivative of cosine t is negative sine t. So what I'll do is go ahead and erase the plus part. And so it's just going to be minus 2 cosine t sine t j. And then plus the derivative of tangent squared t is going to be 2 tangent t. And the derivative of tangent t, of course, is secant squared t. Okay. Alright, so now we found our tangent vector, and now what we want to do is we want to find our tangent vector when t is equal to pi over 4. And so we have 2 sine of pi over 4 cosine pi over 4 I minus 2 times cosine pi over 4 sine pi over 4 j plus 2 tangent pi over 4 secant squared pi over 4. Okay. And so I'm going to have 2 sine of pi over 4 is just square root of 2 over 2. Cosine of pi over 4 is just square root of 2 over 2. I minus 2 times cosine pi over 4 is just the square root of 2 over 2. Sine of pi over 4 is the square root of 2 over 2. J plus 2. Tangent of pi over 4 is just going to be 1. And then secant squared of pi over 4 is going to be just 1 over the square root of 2 over 2 squared. When we work that out, we're going to get 4 over 2, and 4 over 2 is just going to give us 2. And then we have that, so we're just going to multiply. And so our tangent vector at pi over 4 is just going to be, we multiply through, 2's are going to cancel out, square root of 2 times square root of 2 is just 2, 2 over 2 is going to be 1, so we're left with I. Minus, the same thing's going to happen. I don't know why I wrote that cosine right here. We get rid of that when we do the cosine. The square root of 2 over 2. And so we multiply through. 2's cancel out, square root of 2 times square root of 2 is 2 over 2, so minus j. And then 2 times 2 is 4, so plus 4. Okay. So there's our tangent vector at pi over 4, and we want to find the unit tangent vector. So what we're going to do is we're going to need to divide that by the magnitude. So the unit tangent vector is denoted by capital T of t, and we have our tangent vector at pi over 4 over the magnitude. And so we're just going to take all of our components, which is going to be the square root of 1 squared plus negative 1 squared plus 4 squared. And we get I minus j plus 4k all over the square root of 1 plus 1, 16, so 18. And so that's just going to reduce to I minus j plus 4k. 9 times 2 is 18, square root of 9 is 3, so 3 square roots of 2. Alright, and there's our answer. Right, and you can leave it in this format. Another way that you can write this, I'll say or, you can write 1 over 3 square roots of 2, I minus 1 over 3 square roots of 2, j plus 4 over 3 square roots of 2, k. And if you want to rationalize the denominator, you can go ahead and do that. But again, you don't have to, and we seldom ever do that in this class. So you can just keep it the way that it is. Right? I mean, there are multiple ways that you can write this as well. I mean, if you want to, I'll write another one in red. You could also say, well, that's the highlighter. And so you could say, or 1 over 3 square roots of 2, and then you could just have times I minus j plus 4. Okay, I mean, you could write it that way. Right. I'm just about to ask, did anybody have any questions, but this is not class time right now. Alright. This is not live. So if you do have questions, go ahead and make sure that you come to me and ask questions if you have any. I don't expect this section to be too tough. Alright, now, the next one is to find parametric equations for the tangent line to the curve with given parametric equations at the specified point. So we're not looking necessarily just for the tangent vector, we're looking for the tangent line. And if you remember from chapter 12, when we're writing out an actual line, it's going to be defined in R, where we have an initial point plus some vector that's parallel times t. And in this case, we got, if we're doing the parametric equations, it's going to be x is equal to x sub 0, so the x component of our point, plus, our vector, which usually we denote the vector as a, b, c. And so it would be at for the x component. Y would be y sub 0 plus bt, and z would be z sub 0 plus ct. So that's what our answer is going to be in, because we're writing the answer as an actual line. And so we're going to write the parametric equations for that line. So we're not just finding the vector or the tangent vector. What we're really looking for is, what is the tangent line? What is the equation for the tangent line? All right? And so, again, since it's an equation of a line, you don't really need, the r of t, but again, you can see it as that function. So what we're going to do, first, we're given a bunch of parametric equations, and we're given a point. The first thing we want to know is, what point are we talking about? And not just what point, but, what value of t gives us, our point 2 natural log of 4, 1. And so the way that you can find, okay, what, value of t is giving us this is going ahead and, using one of our equations and setting it equal to one of the values. Judging from x, y, and z, the easiest equation to use would be z. It doesn't matter which one you use. I'm just going to use the one that's easiest. Because if z is equal to t, and t for the point, and that is also the component for z is 1, then what we can say is z is equal to t is equal to 1. So we know that we're dealing with the equation of a line when our time is equal to 1. All right, again, you could have used x for that. You could have used y for that. And you would have gotten the same thing. You would have gotten t is equal to 1. But again, z was the one that you wanted to choose because it is, the fastest. All right, so now what we want to do is we want to go ahead and, since we want to do the equation of the equation of the tangent line, we want to find the tangent vector, because that v is going to be parallel, and so we want to be parallel to the tangent vector to actually do the tangent line. So our tangent vector is going to be our vector that we're going to use for our equation. So we're going to go ahead and just take the derivatives of each part. So we have x prime is equal to, and then what we're going to do here, since we have the square root of t squared plus 3, go ahead and put 1/2 in front. T squared plus 3 times negative 1/2 and then multiply by the derivative of the inside, which is 2t. So another way you can look at this is just t divided by the square root of t squared plus 3. Alright, for y, so let's do y prime. How much room do I have? I'll do y prime right here. And so the derivative of natural log is just the derivative of the inside, which is 2t divided by the inside, so t squared plus 3. So that one wasn't too bad. And z prime, that one's real easy. The derivative of just t is going to be 1. All right, so now we have our vector, our tangent vector. And so now what we can do is we can go ahead and find, okay, that's the equation for our tangent vector. Well, what are the actual values for that vector? And so now what we're going to do is we're going to plug in what our t value is. So x prime of 1, again, these could be like x prime of t, y prime of t, z prime of t. You don't have to denote that, but I'm just going to show you that. So, you know, if you want to make sure, you know, why I'm able to write x prime of 1, and that's just, you know, our t value is going to be 1. So we're plugging it in, and we get 1 divided by the square root of 1 plus 3, which is just going to be 1 over the square root of 4, which is just going to give us 1/2. All right, do y prime of 1, and so we're going to get 2 times 1 over 1 squared plus 3, 2 over 4, another 1/2, and z prime of 1 is just going to be 1, because for the tangent vector is always going to be 1, because there is no t to multiply. All right, and so now I have that vector, and so my tangent vector, so like r prime of 1 is 1/2, 1/2, 1. And we're going to use this for our vector part, all right? And we're going to go ahead and use our initial point as our initial point. And so let's go ahead and write this out. So for each parametric equation, we're just going to have x is equal to 2 from the point that's given plus 1/2 t. And again, the 1/2 comes from that component. Y is equal to natural log of 4, again, coming from there, plus 1/2 coming from here, t. And then z is just equal to 1 plus 1t. So just plus t. And there's our parametric equations for the tangent line.